Good afternoon, everyone, and welcome to the latest SCLF webinar. You're very welcome here today. My name is Alison, and I am a member of the SCLF Executive Committee, and I will be hosting today's webinar and looking after the event backstage. So if you do have any technical problems, if you want to just pop them into the question box, and I'll do the best that I can to help you out. You should all have joined on mute today, and your camera is off, so you can sit back and relax and just enjoy today's session. Or remember, I did send out the link if you wanted to sort of like play along with Simon and get the tech to work. If you want to like follow what he's doing on CLEA as you go, then feel free obviously to do that. If you do have to step away for whatever reason, we are recording this session today, so if you need to catch up, then you can do so on our YouTube channel, and I'll put the link for that in the chat in a wee bit. So if you have any comments or questions that you want to put to Simon today, then just put them in the question box. And if we don't manage to get to answer them all live today, because we are going to be a bit tight for time, I think, then we'll try to answer them offline. And last bit of housekeeping is just to say that when you leave the webinar today, you will be offered to fill in a short feedback form. We'd really gratefully appreciate if you could do that. There's also an additional question in there about whether you would be interested in having some more detailed training on using CLEA, a sort of like, you know, the equivalent of a 1 day, but it might be held sort of virtually over a number of days. So if you could give us your feedback on that and sort of express interest in that, then we can see if we can do something about that too. So without further ado, I'll just do the formal introductions. So our speaker today is Simon Firth, and he's going to take us through CLEA and build on the SoBRA webinar, which sort of gave us an introduction to the model. Simon's an independent environmental consultant with 27 years experience in land contamination. Started out as a hydrogeologist, and he's since developed significant expertise in human health and environmental risk assessment, both in the UK and internationally. Simon routinely conducts peer reviews in land contamination risk assessments and is a scrutineer for SoBRA's risk assessor accreditation scheme. He has been instrumental in the development of published generic soil and groundwater screening values for the protection of human health in the UK, including the C4SLs and the SoBRA GAC, and has contributed to various UK guidance documents on risk assessments. He's very well placed to be doing this presentation today. So without further ado, I will hand you over to Simon and let you take it away. Thanks, Simon.
Great. Thank you very much, Alison, and thank you very much to the Scottish Contaminated Land Forum for inviting me to do this webinar today. I'm just going to share my screen. And start the presentation. There's that. There we go. Yes. So yeah, today's presentation is about using CLEA for human health DQRA. Now, if you don't know what DQRA stands for, you're probably in the wrong presentation, because there was the introductory one done by David Dyson for SoBRA about a month or so ago, and I really recommend you know, having a look at that. In fact, there's a bunch of webinars. If I click on this SoBRA website and bring up the SoBRA website here, there's I sort of urge you to look at the SoBRA website, because it has these early career webinars in all sorts of different things, and you can just click on any of these webinars. You know, there's one on ground gas, and there's David Dyson's one on introduction to CLEA, and all sorts of other things on there. So and they're all free, totally free. But it would be good if you join SoBRA as well, if you're gonna look at those. But you don't actually have to be a SoBRA member to get that resource. Yeah, so David Dyson, in his presentation, he really focused on kind of the, you know, how CLEA looks and the different sheets you get in CLEA, and how you would use CLEA to derive generic assessment criteria, I suppose. Today, my presentation is going to focus on how to use CLEA for human health detailed quantitative risk assessments. And so I'm going to do a bit of kind of demonstration using the CLEA model. And by all means, you know, if you've got CLEA open, you could be following along. I believe Alison is recording the this webinar. Yeah, she said that. So you could always replay it and stop it and pause it and to try and kind of follow what I'm doing, because I'll probably have to go quite quickly today to fit everything into an hour. It's quite a lot to get into an hour. The other thing I want to do, I've got a few slides as well. I want to kind of explain what CLEA is doing, what the model's actually doing, and the principles behind human health risk assessment, so that rather than it just being a black box model where you kind of plug in numbers and numbers come out, you've got a better understanding of what the model is actually doing, because I think that's important when you're doing DQRA. Okay, so first of all, just to talk about how the principles behind human health risk assessment. I mean, human health risk assessment, up here at the top of the page, we've got the two main elements. You've got exposure assessment. So that's where you're estimating the dose to a human receptor. And then on the right-hand side, we've got the toxicological assessment. So that's where you would generally be coming up with some sort of acceptable dose, or a health-based guidance value is the kind of generic term for that. And then you would be comparing this estimated dose with your health-based guidance value, which would be your risk characterization. Is the estimated dose above or below that health-based guidance value? But of course, the risk assessment doesn't just finish there, because we have a key part of any risk assessment is consideration of the uncertainties. We need to think about the uncertainties. We need to think of the context and objectives of the risk assessment. Why were we doing the risk assessment in the first place? And we kind of take all that information together, and then we do a risk evaluation. The risk evaluation is where we're asking ourselves, is there an acceptable or an unacceptable risk? Is remediation or risk mitigation required, or is it not warranted? That kind of thing. So that's the overall principle behind human health risk assessment. Oh, hang on, I'll click back on that. Yeah, so I'm just going to illustrate that process with a very simple example. So take this child sitting in the back garden, potentially eating soil, and we know that this soil contains arsenic. So how do we go about doing human health detailed quantitative risk assessment for this receptor? So the first part is the exposure assessment. Is there a source pathway receptor linkage? Well, yes, clearly there is here. We have a source, arsenic, in soil. We have a receptor, the child, and the pathway. In this case, the example I'm going to use is that child eating the soil containing arsenic. So the next part of the exposure assessment is, well, what is the dose to that child? So in order to know that, we need to know what the concentration of arsenic is in the soil and how much soil that child is going to be ingesting, and then we can work out the dose. We also need to then do the toxicological assessment. So this is where we're asking ourselves, okay, what sort of adverse effects could arsenic cause? Could it cause lung cancer? Could it cause bladder cancer? Could it cause problems with the kidneys? Whatever, what problems could it create? And importantly, what dose is required in order to cause those adverse health effects? So that's your toxicological assessment. And by combining those two together, that's your risk characterization. And then we come along to our risk evaluation. The risk evaluation, I said in the previous slide, involves consideration of the uncertainties. And really, we're asking ourselves here, okay, we've estimated a dose to this child, but how confident are we in that dose estimate? How wrong could we be? And then on the toxicological side, how likely is it that that predicted exposure to the receptor is going to cause an adverse health effect? And by answering those two questions, we're able to do a risk evaluation and work out whether there's an unacceptable risk to this child. Okay, now switching to the CLEA model. CLEA obviously stands for Contaminated Land Exposure Assessment. What the CLEA model does, it derives a soil assessment criteria based on chronic health risks for comparison with measured soil concentrations at site. I'm going to explain about that chronic risks in a second. That's typically how we use CLEA, is to derive soil assessment criteria. It could be generic assessment criteria if we're using generic assumptions, or it could be site-specific assessment criteria if we're using site-specific assumptions. But also the CLEA model can be used for what we would call forward modeling, is where you're predicting exposure to a receptor from a known or a measured concentration in soil. And in fact, CLEA, it allows you to put in a measured concentration in soil, or soil vapor, or indoor air or outdoor air concentrations, or concentrations in produce that people are consuming. So that's the two things that CLEA allows us to do. Now, just a word on chronic and acute health risks. So yeah, an important part about the CLEA model is it's really just looking at chronic risks, and chronic risks are risks related to exposure over a long duration, typically greater than a year up to a lifetime. Whereas acute risks is risks related over a short term, typically, you know, a few minutes, hours, up to a day for acute risks. And that is something we can't forget about. Acute risks, the vast majority of cases, don't tend to drive the remediation at site. It tends to be the chronic risks, and that's why I think people tend to focus on the chronic risks. But just, you know, don't forget about acute risks, but remember that CLEA is just looking at those long-term chronic risks. Okay, so how does, thinking of that previous slide of the child eating arsenic and the principles behind human health risk assessment, how does that fit in with the CLEA model? So the CLEA model, it's a model that calculates, as I said, can calculate soil assessment criteria. And there's two aspects to that model. The first one is the exposure modeling part. So CLEA models exposure for up to 9 different exposure pathways. I'm not going to list what the pathways are, because hopefully the majority of you today here will know what those pathways are. But it's things like soil ingestion, dermal contact, consumption of vegetables, vapor inhalation. Okay, so there's, for each one of those pathways is an equation to calculate exposure, and those equations have parameters, and those parameters need to be populated with values, things like, you know, how much soil do you eat, what's your body weight, things like that. So that's exposure modeling aspect. CLEA will take a soil concentration and calculate exposure from that soil concentration. It then compares that exposure with your health-based guidance value. This is the toxicological assessment part. The health-based guidance value generally has been derived normally by others, by authoritative bodies. It could be the UK Health Security Agency, it could be European Food Standards Agency, or the US EPA, or whatever. Some sort of authoritative body has looked at all the available toxicological information for that chemical, and they've used that to derive a health-based guidance value, a dose which is considered to be acceptable. Now, what the CLEA model does, it calculates a soil assessment criteria, and that is the soil concentration at which your average daily exposure to the receptor would equal your health-based guidance value. That's kind of simply put. It's a little bit more complex than that, which I'll come to later, but that's essentially what it's doing. Then, of course, you've got your actual, all this stuff is done without necessarily knowing very much about the site. Then you've got the measured concentrations at your site. And so what you're doing is you're taking those measured concentrations. You might have 10 samples with 10 different concentrations, and you're trying to say, okay, with those 10 concentrations, what is my receptor? What's the kind of average concentration that they're going to be exposed to? So you come up with some sort of representative exposure concentration. You might use statistics, you might not, to do that. And then you're comparing that concentration with this soil assessment criteria. And generally, if your measured soil concentrations are less than the soil assessment criteria, we can assume that the exposure will be less than the health-based guidance value. That's how it works. Okay, now I'm going to get a little bit into the kind of maths behind CLEA. So I know it's a lunchtime slot, so that many people will start switching off already, but just try and stick with me here. As I say, CLEA has got this, exposure modeling part to it, and it estimates the average daily exposure for up to 9 different pathways. And this is a generalized equation here for estimated exposure for each pathway. So the average daily exposure is equal to the exposure rate, that's down here in red, for that pathway, times exposure frequency for that pathway, i.e. the number of days the receptor is being exposed in that way, multiplied by the exposure duration, how many years they're getting exposed to, essentially, divided by their body weight and divided by the averaging time, over what length of time you're going to average that exposure, generally how many years. Now, in the UK, actually, the way we do things, the exposure duration is always equal to the averaging time. So those two cancel each other out. So that simplifies things. So the average daily exposure is simply the exposure rate for the pathway times exposure frequency divided by body weight. That's all there is to it. Now, for each one of these 9 pathways, there's a different equation for the exposure rate. So let's take the soil ingestion first of all. This is a simple equation. So the intake rate here is just equal to the concentration in soil times the soil and dust ingestion rate multiplied by the relative bioavailability of the contaminant in soil, and that's your intake rate. Relatively simple. But some other pathways are more complicated. We have the vapor inhalation indoors. Actually, at first sight, it seems fairly simple. The intake rate is equal to the concentration in indoor air times the volume of air you breathe in a day times the number of hours you're on, breathing that air divided by 24 hours. That's pretty simple. The complicated bit is calculating the concentration in indoor air arising from a soil concentration in the ground. And the CLEA model uses a US EPA Johnson and Essinger model to do this, and that's got a whole bunch of equations. I'm not even showing them all here. I'm only showing a few of them. It's a kind of complicated thing with lots and lots of parameters in there. Another example I want to give you is the consumption of homegrown produce. And I want to give you this example because I want to tell you about the top 2. You might have heard of this top 2 approach for modeling exposure for consumption produce, which is used in the C4SLs. So exposure from produce, there's 2 elements to it. One is there's a kind of uptake of contaminants through the roots into the produce. So if you've got a carrot, the carrot takes the contaminant up through pore water, comes into the root system, and then it's brought up into the carrot, and then we come along, we eat the carrot, and so we're exposed to contaminants in that way. So that's this top equation here. The bottom equation is just the fact that you don't wash your carrot properly, so there's a bit of soil attached to the outside and you get exposed that way. Now, the equations for this intake rate, again, is equal to the concentration in soil times the consumption rate, CR. This is the amount of that produce type. Remembering in CLEA, there are 6 different produce types. You've got, what have you got? You've got tubers, i.e. potatoes, root vegetables, carrots, parsnips. You've got green veg, lettuce, broccoli, cucumber, whatever. And then you've got 3 fruit types. You've got tree fruit, apples, pears, shrub fruit, strawberries. No, shrub fruit would be blackcurrants and brambles, and then herbaceous fruit, strawberries. So those are your 6 produce types. So for each produce type, you're calculating an intake rate, and you're multiplying your soil concentration by the consumption rate for that produce type, multiplied by the homegrown fraction, i.e. if you eat 10 kilograms of potatoes in a year, what fraction of that you're actually growing in your own back garden? And generally in CLEA for residential scenarios, it's assumed to be 2 to 5%, some there or thereabouts. Can't remember the exact numbers, it's something like that. Multiplied by the CF, the concentration factor. That is the ratio between the concentration in soil to the concentration in the vegetable. The higher that concentration factor, the more the plant uptakes the contaminant, the higher the risk. And then the equation for this soil attached produce is exactly the same as this equation. The only difference being, instead of this concentration factor, you've now got SL, which is just the amount of soil attached to the produce. Okay, so both equations use this consumption rate. Now, the soil guideline values, what happens with soil guideline bodies is, to be conservative, they use, for all 6 produce types, they use the 90th percentile consumption rates from a study done in the UK population. So basically it says, right, you know, some people eat a lot of carrots, and some people eat a lot of potatoes, and some people eat a lot of strawberries. So we're going to assume that the kind of that you've got, your receptor eats a lot of potatoes, a lot of carrots, a lot of strawberries, a lot of apples, a lot of pears, and so on. So they use 90th percentile consumption rates for all 6 produce types. But actually, as part of the C4SL project, we decided that that was overly conservative. You know, it's very unlikely you can get an individual that's a big eater on all those produce types. So we used an approach that had been used for radionuclides, you know, radionuclide risk assessment, where you look at the top 2 produce types. So what you do is you use something like CLEA or the equations in CLEA. You actually use those previous equations I showed you on another page to calculate the intake using mean consumption rates or 90th percentile consumption rates for all 6 produce types. And you work out which 2 of those produce types are giving you the biggest exposure. And those 2 produce types, you're going to use the 90th percentile consumption rates when you come to calculate your C4SLs. But for the other produce types, the remaining 4, you're going to use mean consumption rates. Now, we would use something like, let me see if I can just find it here. So I've got a spreadsheet that we used in the C4SL project, and I was suggesting to Alison we make this publicly available. I'm afraid I haven't quite got round to sorting that out yet. I will see if I can get that done, because it's just, all this spreadsheet does is it calculates the consumption rates, the exposure for different contaminant types. So I could say, oh, I'm going to be looking at benzene here, and I would then go into the CLEA model to get my concentration factors that the CLEA model was predicting, or use my empirical concentration factors, and I'll just make up numbers here. You know, if I do this sort of thing, put them into all these produce types, 0.05, 0.06, and I don't know, I've got my faces in the way, which is not a good thing. I don't know if you can see over here highlighted, this is ranking the produce types. We've got the bottom one, which I think is going to be tree fruit, and then the next one up is herbaceous fruit. So for this particular contaminant, I work out that my top 2 produce types are tree fruit and herbaceous fruit. So I'm going to use my 90th percentile consumption rates for the C4SLs for those, and I'll use mean consumption rates for the other 4. Hopefully that makes some sort of sense. Okay, so that's the top 2 produce types. Okay, so I've not gone through all the equations. I'll touch on vapors later on in the webinar. But needless to say, because you've got these 9 different pathways, all of which we've got different equations and different parameters, you end up with the CLEA model needing, you know, a lot of different parameters. So you've got contaminant-specific parameters. Well, you've got your health-based guidance values, of course. CLEA certainly needs those. For some of the contaminants, you will also need background exposure. I'll explain about that in a second. And you also need your relative bioavailability for the oral and inhalation pathway. So that's your kind of toxicological kind of stuff. Then you've got your fate and transport parameters. So that'll be things like how, you know, Henry's law constant, or the air water partition coefficient as it's called in CLEA. Air and water diffusivity, solubility, vapor pressure. These are all things specific to the contaminant that all relate to how it can migrate in the subsurface. Then you've got exposure factors relating to the receptor itself. You know, how much does the receptor weigh? What's their exposure frequency? How much air do they breathe? How much soil do they eat? How much skin is exposed? This kind of thing. And lastly, you've got physical conditions relating to the site. So, for example, your soil properties. What's the soil organic matter? what's the what else have we got here? The soil porosity, the air-fill porosity, water-fill porosity, the bulk density of the soil, and then you've got your building dimensions, building properties, what size the building is, what size the crack around the foundation of the building, what's the pressure differential between the inside of the building, outside the building. This is all to do with the vapor inhalation. I'll talk about this in a second. But needless to say, there's a lot of different parameters that go into the CLEA model. Okay, just a couple of slides on the health-based guidance values. So the soil guideline values, they were based on over there. Yeah, the soil guideline values, the health-based guidance values, guideline values used for the SGVs were called health criteria value, and that they were just sort of defined as the average daily intake that represents minimal or no appreciable risk. Then came along the C4SL project, and the C4SL project defined this new term for a health-based guidance value, which was a low level of toxicological concern, an LLTC. And it didn't, it was sort of higher, slightly higher than the minimal, no appreciable risk. It was representing low risk, but it would still be sufficiently protective of human health, but not quite minimal or no appreciable risk. Now, both HCVs and LLTCs are derived using this same equation. The health-based guidance value equals the point of departure divided by uncertainty factors. Now, the point of departure is something that comes from the toxicological study, and that toxicological study could be a study involving animals, or it could be a study involving humans, you know, a human epidemiological study of workers in a factory. Generally, the point of departure will be something like the dose that was a no observed adverse effect level. You know, the highest dose that didn't lead to any adverse effects, or a lowest observed adverse effect level, the lowest dose that did give adverse effects. Or you could use a slightly more complicated thing called the benchmark dose. And I don't have time to go into that, what that means exactly today, but anyway, that's your point of departure, comes from a toxicological study. Then to come up with a kind of a dose that's seen as being an acceptable dose for using risk assessment, you tend to divide that point of departure by uncertainty factors. And the size of that uncertainty factor is purely relates to how much uncertainty there is in your in the point of departure, really, and how that relates to risks to humans. So you might you'd have a really large uncertainty factor if you had a very poor quality animal study and you were using a kind of lowest observed adverse effect level that led to that was a really serious effect. You know, the half the animals died or whatever. Whereas you'd have a very low uncertainty factor if you were using a human epidemiological study and the adverse effect was a relatively minor effect. So that's basically how these are derived. Now in CLEA, well, health-based guidance values in general tend to be route specific. That's intake route specific. So you generally have a different one for the oral pathway, i.e. ingesting contamination, to inhaling contaminants. Often contaminants can be far more toxic when you inhale them than when you ingest them, because when you ingest them, it's got to get through the stomach lining, and then it's got the kind of the liver is a kind of first pass protection system to get rid of toxins, whereas the lungs doesn't really have the benefit of that. So often health-based guidance values can be lower for inhalation. I mean, strictly speaking, you should have a health-based guidance value for dermal as well, because that's the third route of exposure that's considered in CLEA. But in actual fact, in CLEA and to be honest, internationally, generally the oral health-based guidance value will be applied to dermal exposure. The other thing that we need to determine when it comes to health-based guidance values is whether the health-based guidance value is based on what are called threshold or non-threshold effects. Now, this little graph shows the difference. So this graph is showing kind of dose along the x-axis and response along the y-axis. So response could be, number of animals that have an adverse effect occurring to them. For non-threshold effects, that would be chemical A here. Non-threshold, those are, for example, carcinogens, genotoxic carcinogens. And basically, there's no dose at which there's no risk. Any dose, no matter how small, has some sort of risk associated with it. It's just the higher the dose, the higher the risk. Whereas a threshold compound, which is illustrated by contaminant B here, there's a dose below which there is no adverse effect level. Nothing happens below that dose. Now, in the CLEA model, a health-based guidance value that's based on non-threshold effects, the term given in CLEA is an index dose, or ID for short. And the threshold health-based guidance values, the term given is a tolerable daily intake. You need to know that when you're using CLEA because that's one of the inputs you need to enter. Okay, and then where do we obtain these health-based guidance values for? I think the vast majority of us, myself included, will be using health-based guidance values derived by others. I'm not going to be deriving it myself. You really, you need a toxicologist to derive one because it does get very complicated. So you're looking for some authoritative source to get a health-based guidance value for. Ideally, you would use existing SGV or C4SL reports if they're available. But then we've got other organizations like the European Food Standards Agency, the US EPA, the US Agency for Toxic Substances and Disease Registry, ATSDR, the World Health Organization. Then you've got this RIBM, which is this Dutch organization, Health Canada. These are some of the most common that I'm listing here, which is where you would find these health-based guidance values for. And this is the sort of thing, when you look at, for example, the LQM CIH S4ULs, or the C4SL reports, or the SGVs, these are the kind of places that they're looking to get health-based guidance values. Now, okay, so I've talked about, well, very, very briefly, how CLEA does exposure modeling to calculate an average daily exposure, and then how the health-based guidance values work. So what CLEA does is it actually calculates two assessment criteria, not just one soil assessment criteria, it calculates two. So the first one is the soil concentration at which the average daily exposure for relevant pathways equals the health-based guidance value for the oral route of exposure. When I say relevant pathways, normally that would be the oral and dermal routes of exposure. And then the other assessment criteria is where you're comparing your average daily exposure for relevant pathways to the inhalation health-based guidance value. And there, the relevant pathways would typically be the inhalation pathways. Now I say typically because it's not always the case. You look at things like, well, the C4SL for TC, we're going to be looking at this later a bit. That actually compares the average daily exposure for all pathways with the health-based guidance value for oral, and the average daily exposure for all pathways to the inhalation health-based guidance value. Okay, so there are slight differences. So CLEA calculates these two assessment criteria. Now, then what it can do is if both health-based guidance values are based on what are called systemic health effects, it will combine those two assessment criteria into a slightly lower assessment criteria, and that's the one that you'd use as your assessment criteria for comparing with your measured soil concentrations. Now, what I mean by systemic health effects is the effect occurs away from the point of entry. So if you ingest arsenic and it causes lung cancer because it gets into the bloodstream, gets the lungs, and that's where it does the damage. It uses the blood system to get around. That would be a systemic effect. Whereas as opposed to a localized effect, a localized effect is where the effect is at the tissue at the point of entry. So that could be asbestos, inhalation of asbestos fibers. It causes, you know, lung cancer because of the asbestos at the point of entry in the lungs. So that would be a localized effect. Now, if either of the health-based guidance values are based on a localized effect, then you don't combine the two assessment criteria. You take the lowest of the two assessment criteria as your overall assessment criteria. Right, okay. Now we get on to actually demonstrating CLEA. So I've got two case studies to talk through here. So the first one is we've got elevated concentrations of arsenic and hexavalent chromium within the shallow soil of a site that's going to be redeveloped for, say, 10 houses with gardens. Now, this little box plot here, trying to follow the new CLEA guidance, this shows the concentrations of, you know, summarizes the concentrations of arsenic and hexavalent chromium. So the box plot shows the top bar and the bottom bar is the range in concentrations. The cross is the arithmetic mean concentration, and the sorry, I don't know what's happened to my cursor. And the top of this box is I think is the upper 25th percentile, and the bottom of the box is the lower 75th percentile. Now, I put on the category 4 screen levels here, so you can kind of see, hopefully, that for arsenic, the concentrations we've got are generally, you know, between 60 and 90. They're way above the C4SL, you know, so that's we've got an exceedance. We've got elevated concentrations with respect to our generic screening value. Similar thing for chromium. We've got a C4SL of 21 milligram per kilogram, and we're above those. Okay. So we think, maybe we should be considering doing DQRA. Okay, cue the CLEA model. So let's bring up CLEA. Let's just bring up the CLEA. This is the CLEA that you download from the website. This is the one. If you're now, this would be the time to open up your CLEA model if you can. And what I'm going to do is, first thing I need to do is reproduce those C4SLs. Okay, so it's residential. So I'm going to go to my basic settings. I'm going to choose my residential with produce C4SL. I'm going to apply my settings to the model. And then I just have to wait a little bit until that says this little box comes up and click on OK. Okay, so that's it. I've set my land use and that's automatically chosen all these other things. I then go to my next, sorry, I should have, well, David Dyson in his presentation explained how these buttons work, but you know, you work your way, you're working through these buttons. So I'll ignore report details, that's not actually vital. So I've done my basic settings. Now I need to select my chemicals. So I'm going to select arsenic, but for the C4SLs, there's this kind of weird thing where we do receptor specific LLTC for some contaminants. So because it's residential, my critical receptor is a child, so I have to select the C4SL child. So I'll select arsenic, I'll select chromium child, apply my chemicals. That's okay. And then I go to my find results and I click find assessment criteria. And then that's going to work away and hopefully come up with these assessment criteria. Now you can see I've got these three columns here: oral HCV, inhalation HCV, and combined. This is what I was talking about a couple of slides ago. It calculates two assessment criteria. Now, in the case of both arsenic and chromium, there must be a localized health effect because it's not combining the values. That's something that go into the inputs. So I'm going to take the lowest, and actually it does say here what that would be, the lowest. So oral, 37 milligram per kilogram. Yeah, that is indeed the C4SL for arsenic for residential land use with produce consumption. And then with chromium, the lowest is actually the inhalation, which is 21 milligram per kilogram. But then I'm going to go, get rid of my face again. I'm going to scroll along here and look at these pathways. Now, for arsenic, what we find is that 91% of our exposure is coming from direct soil ingestion. So if we want to do something clever with DQRA, if we want to maybe do DQRA to get a less conservative or a more accurate assessment of risks, it's actually this direct soil ingestion pathway we're going to focus on. For chromium, I look across here and I find that the most important one is the inhalation of dust indoors. Okay, you've got to be slightly careful with these pathway contributions, because actually they only give you the contributions to if you're not combining your assessment criteria, it will only give you the contributions of the kind of risk driving pathway. So you've got to be slight. There is a workaround, but I'm not going to go into that today. We don't have time. But anyway, so needless to say, getting back to the presentation, our key exposure pathways for arsenic are soil and dust ingestion, and for chromium, hexavalent chromium is dust inhalation. Okay, right. So let's start off with arsenic and soil dust ingestion. Let's bring up those equations again for average daily exposure. So the average daily exposure equals intake rate times exposure frequency divided by body weight, and intake rate equals the concentration in soil times the amount of soil you eat times the relative bioavailability. Now, of those, intake rate is kind of cancels out, if you like, and the concentration in soil is what we're trying to find. We're trying to find the soil assessment criteria. So that leaves us with 4 parameters. So when it comes to DQRA, we have got these 4 parameters. We've got to make a change to one or more of those 4 parameters to make a difference to the assessment criteria. So let's take those one at a time. Exposure frequency. Okay, so let's just say we're building new houses. The C4SL and SCBs are all based on a child spending 365 days in the house. Of course, not every child's going to spend 365 days in the house. You know, like many of us, I'm lucky enough to be able to go away on holiday. So maybe I'm not there for 3-4 weeks a year, whatever. But of course, generally, you know, you can't assume that. There's going to be some people where they aren't lucky enough to do that. So it's kind of, maybe you could reduce it a bit, but you're not going to be able to reduce it much. So generally, we tend to keep the 365 days as 365 days. Body weight. Body weight is based on the mean female body weight for a 0 to 6-year-old child. Now, there's not any way we're going to change that, because this is for a house that's not yet been built. We've no idea who's going to live there. We're going to have to stick with that body weight. We've got the soil and dust ingestion rate, which for a residential scenario is assumed to be 100 milligrams per day. Probably conservative, but again, it's very hard for us to justify a lower value, especially for a planning kind of scenario. Easier for part 2A, but and then we have a relative bioavailability in soil. Now, this is the one, probably when it comes to arsenic, this is the one parameter that we think, oh, yeah, maybe that is something we could do on a site-specific basis. So CLEA asks for this relative bioavailability. So it's not just the bioavailability, it's a relative bioavailability. And what that means, it's the ratio of the bioavailability of the contaminant in soil to the bioavailability of the contaminant in the critical study used to derive the health-based guidance value. This is a bit that people often forget. You've got to think about what the bioavailability was in that health-based guidance value. So for arsenic, the oral LLTC for arsenic is based on increased incidence of lung cancer from ingestion of arsenic-contaminated drinking water from a study in Taiwan. Now, it's generally assumed that arsenic in drinking water, it's in the dissolve phase, that it's going to be 100% bioavailable. I mean, that's an assumption, but that's the assumption that's made. So so when we look at that ratio, the relative bioavailability, the bottom bit of the equation is going to be 100%. The top bit of the equation, the bioavailability of the contaminant soil, we can use methods such as the barge UBM method, which estimates bioaccessibility. It's an indicator of bioavailability. But the advantage of the barge UBM over something like the PBET is it's been validated using in vivo data with UK soils. And actually, when you look at that validation, you find there's a really close relationship between bioaccessibility and bioavailability. You know, if you've got 30% bioaccessibility, that more or less means you've got 30% bioavailability. So here's some, I've gone out, I thought, right, that site with the 10 houses, I'm going to go out, I'm going to take some samples. I've taken 5 samples and I've analysed them for the UBM method. And the UBM method gives you 2 answers per sample. It gives you the bioaccessible arsenic in the stomach phase and in the stomach and intestine phase. Two slightly different tests. Generally what's done now, you know, I could be using well, generally what you do is for each sample, you will use the maximum of these two values. So for this one, it'd be 35. For the next sample, it'd be 27. Quite how you then combine the viabilities for the 5 samples is open to debate. I think typically what's done is people will use the maximum, to be conservative, of all the bioavailability testing done at site. But you know, if you've done 200 bioavailability tests, I think you could use statistics rather than the maximum. So but for the purposes of today's exercise, I'm going to use this 35%. So I take my 35% and I divide it by 100%, and that gives me 0.35. Okay, so let's go to the CLEA model. I'm going to go, let's move this over here again. No, wait, sorry. Kind of, yeah, put that down there. Great. I'm going to go back to the guide. Okay, so I'm now going to be doing sort of site-specific DQRA. So I'm going to be using this bottom row now. I mean, I could look at the basic settings and I could say, oh, is there anything different here? Have I got, oh, I don't have a sandy loam soil, I've got a clay soil. But don't forget that for arsenic, the main pathway was soil and dust ingestion, and we've already looked at the parameters that are involved in that. So it's not going to make any difference whether we change the size of the house or the loam type or even the pH. You know, none of this is going to make a difference. All that's going to make a difference is the, what did I say, exposure frequency and body weight. So we can get all this through advanced settings. These 4 buttons in advanced settings lead to every single parameter that's in the CLEA model. So when you're doing DQRA, you know, don't be afraid of the CLEA model. Go in and, you know, change whatever parameter you want. If you change a parameter, I don't remember what that value is. Yeah, if you change the value, it highlights it in pink, so you know you've changed it. But I'm going to go through, and I know that my relative bioavailability, sorry, go back to the menu, is a chemical specific data. So I'll go to my chemical data and I have to scroll right over the other end of the chemical data. Yeah, there we go. Relative bioavailability. Now there's 2. There's one in soil and one in airborne dust. I think you're rarely going to change airborne dust because it's not a test for that. So we'll go with soil. I'll make that 0.35. If I did want to change things like exposure frequency, I'd do that in land use and receptor data. You know, I could change, this is the 365 days. I could reduce that down if I wanted to, but I'm not going to. And then I go back to my find results. So I did have a C4SL37. I'm going to run it again. And I now get the lowest of the 2. I now get 93. Ignore chromium because I haven't made any changes to that. I've gone from 37 to 93 milligram per kilogram just by changing relative bioavailability. Okay, what about chromium? So chromium, we said the main exposure pathway was dust, and that's generally because chromium has got such a low health-based guidance value for inhalation compared to oral, so the dust becomes important. There's 2 parts of dust. There's outdoor dust inhalation and indoor dust inhalation. This is the equation for outdoor dust inhalation. The intake rate is the concentration in soil times this 1 over PEF, I think it's a particle emission factor or something, times the volume of air you breathe, times the number of hours you're on site in a day. 1 over the PEF is basically the predicted dust concentration, the PM10 concentration in outdoor air arising from soil at site. Now, for the residential scenario for the C4SLs, the CLEA calculates this PEF and it ends up being a PM10 concentration of 0.43 microgram per meter cubed. I'll tell you why that's important in a second. Indoor inhalation, it's actually exactly the same equation as this, but it's got this additional part. So it takes the outdoor air concentration plus this indoor air concentration. And the indoor air concentration is given by the transport factor, the soil to dust transport factor, which is the fraction of indoor dust that's derived from the soil outdoors. and it's generally assumed to be 0.5. So you're saying if you take a Hoover bag sample, in theory, half of the dust in that Hoover bag has come from the garden, sort of thing. And it multiplies that by the dust loading factor. That's your indoor PM10. Now, this is the key point. Look at what it assumes to be the indoor PM10, 50 microgram per meter cubed, as opposed to 0.43. Now, I've used a dust monitor in my house. I don't have the cleanest of the house, I have to admit. Not very good at cleaning. But, you know, the dust concentration in my house is about 50 microgram per meter cubed. It's not an unreasonable value. And the reason, you know, houses are dusty places. Whenever you walk about, you're kicking up dust on the carpets and floors. Whenever you do the hoovering, you're just spreading dust all about. So because that's big number, and also because you tend to spend more time indoors, the indoor exposure tends to be much higher than outdoor exposure. And that's what we found with chromium. It was indoor exposure was the most important exposure pathway. The other thing is, because this here tends to be very small compared to this, the parameters that are important for chromium is this soil to dust transport factor, the dust loading factor, the volume of air we breathe, and the time we spend in the house. Now, the volume we breathe, again, for a kind of planning scenario for some future houses, that's kind of set and clear. We're not going to change that. It also assumes that the child's indoors for something like 23 hours a day. I mean, probably overly conservative, but you know, so maybe you could change that. But most people, I think, for a planning scenario, wouldn't. So it just leaves you with these two. Now, maybe you could argue your dust loading factor in your house is going to be lower for some reason, but I think that's unlikely. Most likely would be the soil to dust transport factor. If you've got, I was just thinking, I was doing a site the other day, and it was these apartments, and they had these the tiniest yards. The yard was twice the size of my desk outside the front of the house. That was the only exposed soil that they had, you know, and there was paths going straight across it. It's where they're going to keep the bins, more or less. I think it's pretty conservative to assume in that scenario that half the dust in their house is going to be coming from that tiny patch of soil. So maybe you could reduce it. Justifying that's a harder thing. But for the purposes of this exercise, I will go into CLEA and I'll say, yeah, that's the one thing I'm going to reduce here. So again, it's go back into advanced settings. It's a chemical specific factor. It's right here at the end, this soil to dust transport factor. And let's just say it was 0.2 because we had a tiny little garden. Go to my results, I find my assessment criteria. Let it do its business. Remembering that the C4SL for chromium, hexavalent chromium, was 21, and now it's gone up to 50. Okay. So let's put those site-specific assessment criteria onto this box plots, and we find that our site-specific assessment criteria are greater than the vast majority of our concentrations. Okay, we could do some extra statistics. We could look at UCL 95 concentrations or whatever. That's fine, we can do that. But you know, that's essentially how the DQRAs worked. This actually, what I'm showing you here, this is a risk characterization. We've still got to ask, we've got to do the risk evaluation, the uncertainty assessment. How confident are we in the site-specific assessment criteria? You know, how confident are we in that transport factor? Why did you reduce it from 0.5 to 0.2? You know, how's that justified? Where's your evidence? This sort of thing. And also, how confident are we that the representative exposure concentration is less than the site-specific assessment criteria? You know, this is where the statistics comes in. Have you taken enough samples? Have you taken them in the right place? All these kind of uncertainties we've got to consider. Right, time is pressing on. I've got one more case study to do. I might overrun my presentation by a couple of minutes, but let's see how we go. So, second case study is we've now got a residential site. We're just going to be developing one residential bungalow with a garden, but there's TC contamination in soil. And in the soil samples taken from below 1 meter below ground level, you've got between 10 to 800 micrograms per kilogram of TC. And but in the top meter, we don't have any TC. and we've got a sandy soil with 3% SOM. So I'm going to compare it to my C4SL for 2.5% SOM, which would be the kind of conservative thing to do, which is 20 micrograms per kilogram. Okay, let's just go back to, let's just open up. What I've done is I've taken the CLEA model that, again, you download from the website, but I've populated it, the chemical database here, with values for TC, which I've taken from the C4SL report for TC. Now, I don't have time to tell you exactly how you go about doing that, but everything's in that report that you need, all the health-based guidance values. Oh, sorry, I should say, here's this TDI. This is because the oral one is based on threshold effects, inhalation one's on non-threshold effects, cancer. Slightly weird thing for normally, this is where you compare which sort of routes of intake do you compare your exposures to the health-based guidance value. I said it's normally oral and dermal for the oral health-based guidance value and inhalation for the inhalation health-based guidance value. Actually, for TC it's a bit different. I said before, you're comparing all the exposure to that health-based guidance value and all the exposure for all three routes, you know, dermal, inhalation, oral to the inhalation one. So now I put all those results in, and then I put, parameter about health-based guidance values. Because one of them is a threshold compound, I need to put in, oh, that's what I forgot to say. Sorry, threshold compounds, you do need to put in a background dose as well, this mean daily intake. You don't need to for non-threshold. So I've put in my mean daily intakes, I've put in all my contaminant-specific parameters like air-water partition coefficient, diffusivity coefficients, and so on and so on and so on. Okay, so I've got my contaminant in. I'm going to model my residential with produce, C4SL. Oh, 2.5%. Oh, I'd already set that up, sorry. 2.5%. Oh, incidentally, when you download the model, you'll find you can't change soil organic matter. And there's an easy way around that. You just have to go into review and go, well, I've already done it, but so I can't do it again. But that would say there'd be a button there saying unprotect sheet, and you just press that button, and then you can go in and change that value. So I've done that. I need to select my chemical, so I'm going to put in, should be down at the bottom of the list now. Anything new that you put in is down there at the bottom. I'm going to apply that. There we go. And I'm going to run it. Right, again, we use the lowest of the two, which in this case is this 1.95 e to the minus 2. It's up there, roughly 0.02 milligrams per kilogram. So 20 micrograms per kilogram, which I think is what we said in the presentation. Yeah, 20 micrograms per kilogram. So we're obviously got soil concentrations way above 20 micrograms per kilogram. So, you know, should we do DQRA? Let's just have a look at the pathways. So in the case of TC, we've got two important pathways. We've got the background, okay, so background exposure is counting a lot. And the other one is the inhalation of vapor indoors. So that's the key exposure pathway, really, the inhalation of vapor indoors. Fine, right. Let's go in and make some changes so that we can make this more site specific. I'll just go back to this slide again. So what we got a residential bungalow, and we've got a sandy soil with 3% soil organic matter. Great, okay, I've told the client now, fine, you can pay me money. I'm going to do a DQRA now. This is going to be brilliant. You're going to love this. I'm going to go to my basic settings, and I'm going to say, yeah, okay, yeah, we don't have small terraced house. I'm going to make that a bungalow. Brilliant, yeah, bungalow. Oh, it's not a sandy loam soil, actually, it's a sand soil. Ah, right, I didn't have any TC in the top meter. So the only way people can be exposed to TC is through inhalation of vapors. I can switch off these pathways. I'm going to switch them off. I'm going to switch all those ones off. I'm not going to have any dust either. So I've just got indoor and outdoor inhalation. Oh, and I've got 3% SOM. Brilliant, right, excellent. Anything else? oh, there is something else. So I go to advanced settings and I go to soil and building data. It will have already, oh, sorry, wait a minute. I've just realized I didn't select. There's something you've always got to do, apply settings to the model. I don't think I did that. We'll just do that. I think, looking at the time here, I think I'm going to be another 5 minutes. Sorry about that, folks. I hope that's not an issue. Okay, so I'm going to go to my advanced settings. I'm going to go to soil and build data. What it's done is it's brought in the properties for a sand. It's brought in my building properties for a bungalow. A couple of things I need to do here. When you're doing kind of DQRA, you should always untick this box, this use default soil gas ingress rate, because otherwise it's always going to use this 25 centimeter cube per second, and that can change depending on building type, building properties, and soil type. But the depth to the top of the source is 1 meter, 100 centimeters, indoors and outdoors. So I'm confident. I've made all the changes I need to make. That's fantastic. Right now I can go to my find results, and I'm going to run this. I cannot wait to see the results. Client's going to absolutely love me, because I'm going to, you know, hopefully show that this is not an issue. So I'll let that do its business. And right. That's a shame. Yeah, so now looking at the lowest of the two, I've now got 0.0079. I'm now down to 8 micrograms per meter cubed. I've done my DQRA and I've come out with a value that's less than half what the C4SL was. So, you know, this is a problem. This is a problem, and but it illustrates an important point. The C4SLs and S4ULs, they're not always protective of every scenario, because they make generic assumptions that are normally going to be okay. But in this case, I think it's because we're using a sand soil as the main thing. A sand soil allows more kind of migration of vapors, and so you get a higher risk, so you get a lower site-specific assessment criteria. So, you know, it's always worth kind of doing some trial DQRA runs before you get the client to give you loads of money to do DQRA, because you're going to look awfully embarrassed if, you know, if you're presenting a report like this. Couple last slides about how the vapor inhalation works. So in CLEA, the vapor, indoor vapor intrusion or intrusion of vapors into indoor airspace, it uses this US EPA model, the Johnson-Messenger model, to predict indoor air concentrations. And that model, an important point about it is it assumes that you've got a concrete slab that's just resting on the soil, really. It doesn't have a void underneath it, and it's got a crack running all the way around the slab. And the processes it models is, first of all, if you've got some soil contamination of TC, it first of all models the partitioning from soil to soil vapor. That's the volatilization. It then models diffusion upwards, because you've got high vapor concentration down near the soil source zone, and you've got a low vapor concentration up by the soil surface, so you get diffusive flow, diffusive flux upwards. Then gets into near the footings of the building, and because often with houses you'll have lower pressure in the house than you do outside the house, because people have the heating on or because of wind effects on the outside of the house. Because you get lower pressure in the house, it sucks air in through it. It sucks air in through the windows, through the doors, through the roof space, but also it sucks air down through the soil and up through this crack. And that entrains the TC or the contamination with it and brings it into the house. Then it gets diluted in the house by all this clean air coming through the house. So that's how it works. Now for this case I was giving with the 7.9 microgram per kilogram assessment criteria for TC for the new bungalow, it's maybe quite likely that the bungalow is not going to have a slab on soil. I mean, often houses are built with a suspended floor, block and beam floor. And this figure kind of illustrates the difference there. With the kind of the Johnson-Messenger model, you get this diffusion upwards, and then the advective flow brings these kind of relatively high concentrations of contaminants up into the house. It gives relatively high risk. If you've got a subfloor void that's ventilated with air bricks and you get this fresh airflow through that subfloor void, what happens is you get a huge amount of dilution of the contaminants in the subfloor void, so the concentrations are reduced a lot before they move up into the house. So the risk is going to be a lot lower than predicted from the Johnson-Ettinger model, you know. So if you've got a new build house, ventilated subfloor void, CLEA is going to be conservative. One thing to be careful of though, that is on the assumption that you've got the air bricks are effective. They do allow airflow through those air bricks. I mean, I was doing an assessment recently, and there were some old Victorian properties, and the air bricks were all blocked up, and the floor here was basically soil, and then you had wooden floorboards. That is actually much higher risk than the Johnson-Ettinger model, because you've got diffusion of contaminants straight up into the house with nothing really stopping it. So you know, you have to think about those things. There are methods available for looking at these air bricks. You've got this Steve Wilson's method, paper 2008. I've given the sort of reference there that you could have a look at. Okay, that's it. I've just got a few key points to make. Sorry to overrun. Yes, sorry, I may have forgot to mention the CLEA SR2 and SR3 documents. So the CLEA model has got these two documents, two reports that go with it. They explain that SR2 explains how to derive a health-based guidance value. SR3 explains all about all the exposure modeling in CLEA. If you're going to do DQRA, you have to read those. And if you're going to go for a SoBRA accreditation in DQRA for human health, you know, you're going to need to know that you're going to have read and understood these and be familiar with them. So I do encourage you to read those. Don't be afraid of the CLEA model. You know, play with it. You're not going to break it. You can just download a new version off the website, or keep a sort of fresh version on the computer. Have a little play with it. Change some parameters for a given, you know, set up a scenario, change some parameters, and think about why is that changing or not changing the results. Think about what the key exposure pathways are, and what the equations are, and what the parameters are, and why it's working. That is going to serve you so well in DQRA. Focus your DQRA on the risk-driving pathways. Don't worry about what the crack size is for arsenic or chromium. It's not important, you know. Do some initial model runs to determine whether DQRA would be worthwhile, as the example I gave there for TCE. And don't forget that it's not just about risk characterization. It's not just coming up with a site-specific assessment criteria and comparing it with measured concentrations. That's risk characterization. You need to then go on and do risk evaluation. What are the uncertainties? What are those key uncertainties? And how confident are we in our conclusions? You know, when we say to the client, oh, there's a significant risk here, you need to spend £3 million remediating the site, are we sure about that? Are we absolutely confident about that? You know, or likewise, if we're saying, oh, there's not a problem here, are we sure there's not going to be health effects to people living in those houses? Okay, well, sorry to overrun. Thank you very much for listening. I'm here for whatever, so just ask me some questions. I realise also, Alison, I forgot to run the poll.
Yeah, no, it's okay. Thanks very much, Simon, for that. Simon says we will just hang about and we've only got a couple of questions, so we will do them. So if you do need to nip off, then you can always catch up on the YouTube channel later on. But one question that's come in is someone would like to know the differences in using the barge bioaccessibility information for lead compared to with arsenic.
Right, yeah, that's a really good question. Do you know what? I was going to start off when I was writing this presentation, I was going to use lead instead of arsenic, and then I thought, oh God, lead's a bit complicated, you know. And the thing is, the good thing about arsenic and why arsenic works really well with the UBM is because you've got this, it's reasonable to make this assumption that the toxicological study, the health-based guidance value, is based on a tox study that's based on 100% bioavailability. The LLTC for lead and the C4SL is actually it's been calculated using the, for the child anyway, using the US EPA IEUBK model to try and predict what dose of lead would give a certain blood lead concentration. And it's that dose, the blood lead concentration that's deemed to be acceptable is 3.5 micrograms per deciliter. And so the IEUBK model has been used to calculate this dose, and that the dose that's used in the CLEA model is the equivalent dietary dose. Now, the bioavailability, in theory, the bioavailability of lead in the diet is 50%, not 100%. And for the lead C4SL, it's assumed that the relative bioavailability is 60%. And that's because it's, if you read the C4SL report, it says the US EPA assumed that the bioavailability in the diet of lead is 50%, and the bioavailability in soil is 30%. So it's 30 divided by 50, which is 0.6. Yeah, so then you've got your bioaccessible UBM barge method, and that's has been validated again really well for lead. So if you've got 50% bioaccessibility for lead, the pigs, when they looked at the pigs that they tested, the bioavailability in those pigs was 50%. So there's kind of a 1-to-1 relationship. So strictly speaking, if you get kind of 60% bioavailability from the UBM method, then you would divide 60% by 50%, which would be 1.2, which would actually give you an even more conservative result. Practically speaking, though, in the C4SL report, we've kind of said, oh, well, we're using 60% relative bioavailability. It turns out that most soils in UK, when you look at the kind of average bioaccessibility, sorry, from the UBM, it's about 60%, and that seems to kind of fit. But it's not a really nice, neat relationship. So I would say that if it was me, I'd say, okay, I'm going to do the UBM, and if I get 30% on my UBM rather than 60%, I'm going to make my relative bioavailability 30% divided by 50%, which is no, sorry, not 30. Sorry, I'm going to do half. What is I'm going to assume there's a direct relationship between the UBM bioaccessibility method and the relative bioavailability in CLEA. So if I get 30%, I'm going to put 0.3 into CLEA, but there is uncertainty associated with that, more uncertainty with an arsenic. So I would just kind of be a bit conscious of that. So I don't know if that helps answer the question, but you would just, it's a kind of harder one, and you need to think about it. Read what's in the C4SL report, and yeah, there's not a straightforward answer, and I don't even quite know what's the right thing to do, but that's what I would do.
Thank you. Can I maybe ask you to maybe briefly explain the main differences between the sort of published health-based guidance values, so like between the C4SLs, your Atkins at risk, and like your S4ULs, and in particular whether there's any of those which would be more appropriate in a sort of Scottish context, bearing in mind the differences in the legislation and the adoption of the C4SLs in Scotland, or lack of.
Right, yeah, I mean, okay, in that point, it's certainly easier in England because the land LCRM pages, the land contamination risk management pages, what the updated CLEA 11 on the well, those pages, are they the same in Scotland? I mean, are they? Sorry, do they apply in Scotland?
They haven't been formally adopted in
right.
Scotland yet.
Got you. So of course in England, it actually specifically says there, if you've got a C4SL for a contaminant and an SGV for a contaminant, you should use the C4SL. So they've made that clear in planning, whatever. That's what you should use. I mean, there's no doubt that the X4ULs are well, they represent a lower risk, although they maybe don't have the same level of toxicological kind of weight behind them, I suppose. I mean, the C4SLs have gone through, you know, they've been kind of reviewed by UK Health Security Agency and Environment Agency and been produced by toxicologists. So I guess that's a kind of, you know, one disadvantage of the S4ULs and the at-risk values. Oh, sorry, I should probably start off by answering the bit of the question what the differences actually are. So the C4SLs, you've got C4SLs which were, we took the SGVs and we made some differences to the exposure modeling parameters. There were just 4 parameters. We updated vapor inhalation rates, made them a bit less conservative for residential scenarios. We changed dermal exposure factors for residential scenarios, and we invoked this top 2 produce. So it kind of mostly the changes related on exposure to the residential. I think actually inhalation also affected commercial, I think. Those are exposure changes, not huge. The toxicological toxicity was different. So we went from this minimal risk health criterion value to this low level of toxicological concern. In some cases, there wasn't a change, for example, with arsenic. That's why the S4UL for arsenic is the same as the C4SL for arsenic. But for things like benzoate pyrene as a surrogate marker for pHs, we kind of went from you know, we kind of multiplied. The LLTC was kind of 4 times higher than the minimal risk value. You know, that was the biggest change we'd have. So yeah, we're definitely using less conservative toxicological health-based guidance values. Now, the Atkins at-risk values, I believe, have made all the changes to the exposure, but just haven't changed. They've stuck with these minimal risk health criterion values. You know, so for example, for carcinogen, they will be basing their health-based guidance value on an excess lifetime cancer risk of 1 in 100,000, whereas the C4SLs are based on 1 in 50,000, twice the risk. The S4ULs, they are similar to that risk, but they didn't quite make all the exposure changes. They didn't do the top 2. So they stuck with the 90th percentile consumption rates for all 6 produce types, rather than working out which are the 2 with the top. So they didn't invoke that. So the S4ULs are kind of more conservative than the Atkins at-risk values. Yeah, in terms of using in Scotland, I mean, I guess it's I mean, in a way, to be honest, it's a policy. It should be a policy decision, really. Because you know, it's the policymakers who decide what the level of risk that should be acceptable. I think that's why it was slightly frustrating in England that it took so long for the policymakers to actually be really open about the C4SL should be used in all different scenarios, and now that's happened. So that's, I think, simplified things a lot. Yeah.
I think the thing that is important that people understand what is included in all these different assessment criteria that might, you know, be coming across regulators' desks or whatever, and it's important that they understand how they've been derived and what risk levels have been used and what parameters have been included and what's been excluded. So I think just even having just a wee outline on that today, I think has been really useful to folk. As I said, in the questionnaire that you'll get at the end, the feedback form, I have asked for people to indicate if they would want some more detailed training. Obviously, this is just a 1-hour webinar. It's turned into 1 hour 20 minutes, but we'll probably just leave it there for today. It just remains for me to say thank you very much, Simon, for your time. It's great how people give their time to sort of help others in the community, in the contaminated land community. So thank you very much. And we'll just close off there. So if you just keep a wee eye out on our mailings and stuff for the next webinar, and also the SoBRA website as well, because they're all being run through this platform too. So we're helping them out to deliver their early careers webinars as well. So thank you very much, everyone, for coming along today, and we'll see you next time. Thank you.
Thank you.